Hello everyone. In my previous session, I had discussed one terminology, the grazing phenomena. So I would like to tell you also something about this grazing phenomena. Actually, at this point, when the wave is entering, then it is the denser medium and it is the rarer medium. So the wave is reflected from this point. That means away from the normal. The wave is deviating from away from the normal. And again, in similar fashion, at this point, this particular layer will considered to be denser one and this is rare one. So again the wave will move away from the normal. Okay, so if you consider this as a normal, so it will move away from the normal. Now at this point, okay, this is the highest maximum achievable point, and at this point the angle of refraction will be equal to the 90 degree actually. So this is called the critical angle actually. So critical angle, when the angle of incidence is called critical angle, when the angle of refraction is 90 degree. Okay, this is why it is called grazing phenomena. So actually in your optics class, you know very well that when the angle of incidence is such that the angle of refraction is equal to, suppose this is here, 90 degree. Okay, so you know these things. This is your I, angle of incidence, and this is your angle of refraction. So this is equal to 90 degree. So when the wave is incidenting and it is moving from one medium to other medium such that the angle of refraction is equal to 90 degree, then the wave will not move from one medium to other medium. Rather, grazing phenomena will occur. This process is called the grazing. Grazing means parallel to x-axis. That means the wave will not further move to the other medium. Rather, the total internal reflection will take place and the wave will return back to its original medium. So that is why I have taken here the help of this grazing phenomena, that at this point of time, which is the maximum achievable point, further there will be no refraction which will take place. Instead of that, the wave will return back to its original mode, that is the earthward. The wave will come earthward. Okay, because at this point angle of refraction is 90 degree, or you can say you will get the component which is parallel to the x-axis. So this point of the angle of incidence becomes critical angle. So what is the definition of critical angle? Critical angle is that angle when the angle of refraction becomes 90 degree. Okay, and the grazing phenomena means parallel to x-axis and the wave will return back to it. Now one important point which I had discussed with the definition of ionospheric layer, that it allows us to communicate in between 2 to 30 megahertz. Now what will happen if we allow to transmit the electromagnetic wave greater than 30 megahertz? Then lambda is equal to actually c by f. So if you are increasing the value of f, then lambda will be shorter and shorter. Okay, so this is what the case is. If you increase the frequency more than 30 megahertz, then the wave length will be so short that it will impinge or it will lost inside the ionospheric belt or ionospheric thickness, and it will not return back to the different point. That is why I have mentioned that wave will lost its identity. So is it clear to you that in between 2 to 30 megahertz, it has practically seen that the wave is returning back after successive refraction inside the ionospheric layer, whereas if you increase the frequency more than 30 megahertz, then the lambda is very short, and as a reason that lambda will be very short, as a reason that the wave will actually penetrate inside the ionospheric layer. It will lost its identity and no more further communication will take place because the wave will not return back to earth different point. So this is what the entire mechanism of this ionospheric wave propagation. Now I would like to also elaborate the point-to-point communication, because many times this ionospheric wave propagation is also termed as point-to-point communication. Why? So I have drawn here Tx as transmitter, Rx as the receiver. Point-to-point communication here because this is one point on the earth surface and this is the other point of the earth surface. So this is why it is called point-to-point communication, because communication is going on via ionospheric layer from one point to another point. This is why it is called point-to-point communication. Now one more thing associated with this point-to-point communication definition is single and multiple Hopf. Means how can you increase the geographical distance of ionospheric wave by increasing the multiple Hopf. So I would like to discuss here single and multiple Hopf reflection for long distance communication. Suppose you consider here these 2 points Tx and the Rx, and you just consider here Tx1 and the Rx1. So that means, and this is your ionospheric layer. So in one case, what is happening from here to here, Tx1 and Rx1, the wave is going up. Okay, the wave is going up inside the ionospheric layer and it is reflecting back to that different point. So this is Rx1. So that means this is Earth surface. So this Tx1 to Rx1 is actually the distance covered by the ionospheric wave propagation. So this is in one hope. This is called the single hope. The wave is going up and is coming back to the Rx1 point, Earth different point. So that is why the distance covered in between Tx and Rx1 is equal to the single hope distance. Okay, whereas you can see that I have drawn also the another diagram in which I have shown multiple hope. Okay, just try to understand. This is your Tx. So from Tx the wave is going up inside the ionosphere and it is coming back to the Earth surface, but it has not got stopped here. Rather, after reaching to this point, again the wave is going up inside the ionospheric layer and again it is reflecting back to the Earth different point. So in this way, from Tx to this point, say P, and again from P to this point and reflecting back to this point, that is Rx. So in this way you can increase the geographical distance. Okay, so through ionospheric wave propagation you can increase the larger geographical distance or the coverage area by increasing the multiple hope. Here we are using the two hope. This is first ground reflected. After ground reflection, again this is a second hope. So in this picture or in this diagram, it is very clear what do you mean by the single hope and the multi-hope communication. So this basically ionospheric wave propagation supports us that if you increase the multiple hope, then you can increase the larger geographical area. Okay, so this is one hope and this is the second hope. The Tx and Rx is giving you the larger distance or the larger coverage area compared to that of this Tx and Rx, which is Tx1 and Rx1, which is a single hope. So this is why it is called multiple hope and the single hope communication as well, which is associated with this ionospheric wave propagations. So in my next session, I will start the another mode of communication, that is a space wave or the tropospheric wave communication. Thank you.